Okay, so the last thing we're going to talk about in this chapter is something called intermolecular forces. So at this point, you should be good at figuring out what kind of bond something has. Polar covalent, nonpolar covalent, or ionic. That's kind of crucial because what we're dealing with now is we're talking about how things interact on a larger scale than just within the molecule itself. We're talking between molecules. We also need to know whether or not something has a molecular dipole, or it's a polar molecule. That's what we did in the last lesson. So we need to know both of those things in order to be able to answer this. So intermolecular forces basically are the explanation for why anything is a solid, a liquid, or a gas at any given temperature. It's the magnet that holds all liquids and solids together. And they're really kind of important. So a couple of definitions. Intra is within. So an intramolecular means inside one molecule. That would be what holds the molecule itself together. So if I'm looking at water, I'm looking at these guys right here. Those are polar covalent bonds. Based on electronegativity, the electrons are not shared equally, but that's what holds the molecule itself, the atoms, together. A polar covalent bond. Intermolecular forces are what hold. Did I not show the definition of that? I guess I didn't. Intermolecular forces are what hold molecules together, two different molecules together. There's three types of them. There's ion dipole, dipole-dipole, and then there's a specialized version of that called hydrogen bonding, and then LDF. So now we're not talking about inside the water molecule. We're not talking about the polar covalent bonds. We're talking about one water molecule with another water molecule. What holds them together? And this is where we get all of our liquids and solids from, is because H2O and H2Os are attracted to each other and they stick like a magnet. Okay, we're talking about these three different kinds of intermolecular forces. So the first one's ion dipole. So an ionic substance, this is one of those ones that was greater than 1.6 electronegativity difference. And they are made out of ions, meaning one of them is a positive charge, one of them is a negative charge. And then you have one with a negative charge and one with a positive charge. And that's what holds them together. That's their glue, is the fact that the electrons completely transfer to the more negative atom. And that holds them together, the fact that one's a positive charge and one's a negative charge. And water, if you remember, has a dipole moment because it is a bent structure. One end of it's negative, one end of it's positive. And when it comes in contact with something that's ionic, what happens is this negative end is attracted to that positive end. That is an ion dipole force. Ion dipole force. They're attracted together. Opposite charges attract. And this is what makes ionic substances dissolve in water. This is why salt dissolves in water. It's because the water comes along, sees that little positive, pulls the positive off, and they're attracted to each other. Okay, so here's what it looks like. These are my water molecules, and again, I'm not showing you the O and the H's because all I'm worried about is one end of it is negative, one end of it is positive, and they are attracted to this. That is an ion dipole force. The positive end of the water and the negative end of the water, positive end is attracted to the negative ion, and so you get an ion dipole force. So this is what it looks like. Remember, water, negative here, positive on this end. It's attracted to the negative, attracted to the positive. That's what an ion dipole force. So water lines up and it's attracted. What happens is, here's my sodium chloride. Here's my little water molecules, my little negatives and my little positives. And they come along. A little positive is going to be attracted here. The little negative is going to be attracted here. And they literally pull off an atom at a time when they line up. Okay, there's the negatives one lining up. And what happens is when they pull off one of these atoms, there's the sodium, positively charged, and here's the negative atom, end, negative, and here's the positive end, attracted to the negative. This attraction between these guys is the ion dipole force, between the ion on one thing and the dipole on another. Okay, dipole-dipole forces are when you have two different molecules that are polar molecules. So if I have O and H, come along, negative, positive, and along comes another OH with its negative end and its positive end. These guys are going to attract each other. That's a dipole-dipole force. Two different molecules that have permanent polarities come in contact with each other and they attract each other. Opposites attract. It's the attractive force between two different molecules. So if this is my water, here's my oxygen, and here's my hydrogens. And then here's my hydrogens, and there's my oxygen. And this is the dipole-dipole force. The attraction between one end on one and the other end on the other. Not inside the molecule, between the two molecules. Hydrogen bonding is a special version of this. It does the same kind of an idea. The difference is the hydrogen atom on one molecule has a polar covalent bond to something that is extremely electronegative. If you look back at the chart, N, O, and F have one of the highest values of electronegativities. And so the hydrogen attached to those three guys is essentially giving up its electron. It pulls the NO and F pull the electrons away from the hydrogen, and basically what you have is you have the nucleus, because hydrogen only has one electron. And if it takes that one electron and it gives it to these guys, all you have left is a nucleus. It's really, really small. And because it's really, really small, it can get very close to the negative end of another molecule. And again, this is Coulomb's law. The closer they are together, the stronger that attractive force is. So, water is the perfect example. Okay, I've got the negative end, the positive end. I've got the negative end and the positive end. When this hydrogen atom gets very close to those lone pairs, this is a hydrogen bond. This hydrogen getting very close to those lone pairs is a hydrogen bond. This is a polar covalent bond between oxygen and hydrogen. It is not. This is not a hydrogen bond. And that's what everybody thinks. It is a polar covalent bond based on the electronegativity differences of H and O. Hydrogen bond is when one molecule is attracted to another molecule based on different charges. Hydrogen bonding is really important for water. It has hydrogen bonding as its strongest intermolecular attractive force. There are two hydrogen atoms available to form those strong hydrogen bonds, so water is extremely attracted to other water molecules. That's why water tends to be a liquid at room temperature. It has a relatively high melting and boiling point compared to other things of its mass. This also explains why solid water floats on top of liquid water, because when they line up as a liquid, they have a lot of less space than they do as a solid. So in a liquid, the molecules can get closer to each other, it's more dense. As a solid, the molecules line up according to their intermolecular attractive forces and freeze in place, literally, and it's less dense and it floats. Most substances, the solid form, is more dense than the liquid form. So this is the solid. See how it's got all this empty space when they line up with their hydrogen bonds? When it turns into a liquid, they get a lot closer together, and it actually decreases the volume, which increases the density. The last of our intermolecular attractive forces is called London dispersion forces, LDF for abbreviation. And these are attractive forces between two molecules that's caused by a temporary dipole. Okay, the dipole-dipole force is permanent. It's based on structure. LDFs are temporary because they are fleeting. They're very weak in strength. They don't last very long. And as the temperature drops, they do get a little stronger, or if you're talking of big molecules, bigger and bigger molecules, it gets a little bit stronger. So the idea is helium has 2 protons and 2 electrons. And if at some moment in time, it's called instantaneous, okay, creates an instantaneous dipole, the electrons line up over here, you would get a negative end and a positive end. And if you took that molecule just for that second while those electrons are distributed unevenly, and you had your negative and your positive, then they got closer to another one, they would induce a dipole. They would force the electrons, because this is positive, it'd pull the electrons over, and this is the LDF force. Positive on one, negative on the other. It doesn't last very long because it's instantaneous. Those electrons are moving and moving and moving. As the temperature drops, they don't move as fast, and so it becomes a little bit stronger because they last a little bit longer. Or if the molecule is enormous, like iodine, then you can distribute that charge over a much bigger area and it lasts a lot longer. So London dispersion forces are a temporary dipole that induces a dipole, and it's the attractive force between two different molecules based on charge. So the properties that affect it predominantly is boiling point, melting point, but also the ability to dissolve in water. And in order to dissolve in water, pretty much everything else that dissolves in water has to have a dipole. So it can be ionic or it can be polar molecule. That's where the term like dissolves like comes. Boiling point and melting point, very important. Okay, and we talked about this when we were doing heat calculations. It takes energy to break apart those forces. The stronger those forces are, so if you're talking water with hydrogen bonding compared to CO2, which all it has is LDF, this one is much easier to break apart because it's so weak, so it doesn't take as much energy, and so this stuff will boil and melt much lower than water will, because water has a stronger intermolecular force, and the stronger the force, the higher the melting and boiling points. Strong forces tend to be solids at room temperature, medium tend to be liquids, weak tend to be gases, but there are exceptions to all of those. So that's just kind of very ballpark, rough idea. Okay, and then the ability to conduct electricity. Ionic substances, so things like NaCl, can conduct electricity if they're dissolved in water because they turn into ions, or if they're melted because they turn into ions and they're free to move. So boiling point in a liquid, molecules are packed close together, and it takes they're moving randomly, but they're attracted to each other by those intermolecular attractive forces. As the temperature increases, the molecules move faster and faster and faster, and as they move faster and faster, eventually they have enough kinetic energy that the forces of attraction between the molecules break, and they go from being a liquid to a gas. They completely separate. The higher the forces of attraction, the stronger the forces of attraction, the higher the boiling point. So if you look at this chart, you might notice that, in general, they increase all along in here. These guys are all dipole-dipole forces. But as they get larger, molecules, the dipole-dipole force strengthens. But if you notice within those groups, these guys are higher than anybody else in their own group. And that's because these guys have hydrogen bonding. And hydrogen bonding is greater than dipole-dipole. Generally speaking, it's greater. It's stronger. Oops, let me erase the ink. So water has a very high boiling point compared to most other polar molecules because it has hydrogen bonding. Same thing for HF and same thing for NH3. Without hydrogen bonding, water would be a gas at room temperature, and life on planet Earth would not exist. So, quick summary of the intermolecular attractive forces. There's ion dipole. That's why salt dissolves in water. The positive pole on water attracts the negative ion. The negative pole on water attracts the cation. Dipole-dipole is anytime you have two molecules with permanent dipoles because of their structure and their bond type. Hydrogen bonding is a special version of it where NO and F is attached to a hydrogen and it's attracted to another NO or an F on another molecule. And then LDF is temporary. But again, it's a positive attraction and a negative attraction, two things. So ionic substance in water is ion dipole. A polar molecule with NO or F is hydrogen bonding. Polar molecule without the H bonded to an N or F is dipole-dipole, and a nonpolar molecule is LDF. The strength of the attractive force increases this way. Everything you notice has LDF. Okay, hydrogen bonding has dipole-dipole in addition because it's a polar molecule. But LDF, that's all it's got. It's got nothing else. And all it has is that little weak strength.